Okay, so we're going to bring in Dinesh and Mark here. Thank you for patiently waiting.
Good morning, good afternoon. I think, where are you two calling in from?
So we're also in England. So we're more south than Ashley. So we're in just outside London.
This is, I just see a meetup happening in the near future when we can all get together and do this thing in person in somewhere between London and Manchester. This is great. So, all right. So this is our next talk, and you both join us from Civo, yeah?
That's right.
Okay. Well, we can duck out. Let you introduce yourself and your topic, and and we'll put your slides up. Do you have slides?
Yeah, I'll just share my.
Okay. All right. We'll start that out. We're gonna, duck out and take it away.
Okay. Hopefully everyone can see that. If Dinesh, you give me a thumbs up, can you see it?
Yeah, they're up for me. I can see them.
Cool. All right, just to kick things off. So hi everyone, I'm Mark Boost. Excited to be here today presenting our talk on going straight to the edge. We'll be covering a few topics around edge computing, in particular, why edge computing, the advantages and disadvantages of edge computing, and then a deeper dive into some of the challenges when moving towards the edge. And I was chatting to Dinesh earlier, actually, when we do all our internal company all hands meetings, he always tends to get the slot at the end, and then he gets pushed out with about 5 minutes out of an hour to present. So I've promised him on this talk that I'll get through my bit as quick as possible, and then he can do his tech part after that. So yeah, formal introductions first. As I mentioned, I'm Mark Boost, CEO of Civo, and I'm joined by Dinesh Majrekar, CTO of Civo. And we've been working together in the hosting industry for over 10 years now. In the previous life, we built the 5th largest hosting company in the UK. We've built data centers together as well, our own data centers. We've launched networks across the UK in terms of MPLS networks, launched a cybersecurity business as well. So we've been involved in lots of different tech areas. But our latest venture is Civo. It's been operating for about 3 or 4 years now. We're a cloud computing provider focused purely on Kubernetes. My background itself, I've been involved in computing since the sort of 90s, where I was a developer. But back then, we used to call ourselves programmers rather than developers. But nowadays, I get more sucked into the commercial aspects of the business, and I leave the techie stuff to Dinesh. So to kick things off, what is edge computing? A common definition is edge computing places computing resources as close as possible to the physical location of the user or the source of the data. And an example of that is moving application workloads from the cloud to remote locations such as factory floors, warehouses, distribution centers, and retail stores. And Dinesh will get a bit more into some of the specific use cases around that. So I won't touch too much more on that at this stage. But the question is why? Why edge computing? And why do we want to move workloads closer to the edge? And there's a very simple reason for that. It's because the speed of light simply isn't fast enough. And that's even though it travels at 300 million meters per second, it's still not fast enough. And what I mean by that is latency. And what's interesting is we've kind of gone full circle here. There's been in more recent years, there's been a huge rush to the cloud. Before the cloud existed, everything was placed in the data center or in people's on-premises locations. We've had this huge rush to the cloud, and now we're starting to see some limitations in what the cloud offers, especially with the kind of explosion of IoT and things like that. And the main thing that's a challenge is latency. And as you can see from the diagram on the screen, latency from say, New York to Auckland is 251 milliseconds. And even to LA from New York is 72 milliseconds. And really in a new world of mobile gaming, smart cities, smart homes, automated vehicles, robots, all that kind of stuff that's to come, this delay in transmission of data simply won't be good enough. So it's proving a lot more challenging when we take the traditional kind of cloud model. So edge computing is really that paradigm shift away from working into a new way to cater for those billions of IoT devices that we might see in the future. So when thinking about what edge computing is, I like to think about it as being similar to what a content delivery network did for static files. Historically, those static files kind of lived in a single data center, and users from all over the world went to that single data center to access that content. And that's very inefficient because of the latency involved in collecting those static images. And for websites like e-commerce websites, when every page load count really matters, it's really important to have that instant response. And so what CDNs really did was to bring that content closer to the user by caching that content locally at more local data centers where the users that are accessing it belong. So much like that, edge computing is doing a similar thing, but instead it's using executable code. You can run executable code at these edge locations rather than just static images. And that presents a better and faster experience for the end user or the edge device that is accessing it. So there's obviously these huge speed advantages through latency, but also one of the big challenges with cloud computing is moving data around is very expensive. So what edge computing allows us to do is reduce the size of the kind of bandwidth requirements that we have to the cloud, do a lot more of the processing locally, and only send the data that we need up to the cloud. And this reduces cost and data transfer costs, and even WAN links size of WAN links that we might need in the future. So one of the interesting things, as we all know, the cloud's the latest thing, but back in the 90s, the concept of edge computing that's when it actually came around. But it's interesting how we've now gone full circle in regard to sort of coming back there. But really what's starting to change that is things like 5G. And it's really that, again, that latency and that speed that's really changing things. And you can see from the two images that I've got on the screen, the first one on the left is showing an actual speed test that I did recently on my phone on a 5G network, where I was getting a ping time of 21 milliseconds compared to a 4G ping time of 31 milliseconds, and then huge advantages on download speeds as well, and double the upload speed. And already they're averaging across the kind of world 300 to 400 megabits per second for 5G, and theoretically speeds can get to well over 10 gig, and that latency can get as low as 1 millisecond. And really what's going to start to happen is, as carriers build more towers to access 5G that are closer to users, that latency is going to come down and that speed's going to go up over time. So things are going to get faster and faster and faster as the investment goes into 5G. But one of the interesting things around 5G as well is that there's an opportunity to actually launch private 5G networks that are unlicensed, where historically with 4G and 3G, there was a limited amount of spectrum license that only large telcos were able to access and pay lots of money to access that. But with 5G, anyone can use 5G privately as well. So you could potentially have a 5G network, say in a warehouse, with all the devices communicating over 5G without having to license anything. And that gives those huge potential speed improvements for things like edge devices, IoT devices, and smart factories and things. So just going to touch on a few advantages and disadvantages of edge computing, and I know Dinesh might elaborate on some of these, but I've already mentioned latency. That's a huge advantage in terms of speed of response. Lower bandwidth and data transfer costs is a big one, because you do a lot more of the processing at the edge location. Performance, because you can spec the exact hardware you need for the job, and whereas the cloud, you have more limited options on what you can specify. Security, which can be an advantage and a disadvantage, but I'll cover that in disadvantages as well. But as an advantage, you have full control over your own security. So if you put in place very good practices, you can ensure it's very secure. And data sovereignty, you know exactly where your data resides. And sometimes I always get the feeling in certain clouds, you wonder where your data's ended up. Where's it being backed up to, and things like that. Is it accidentally going into the wrong place? But if it's deployed at the edge, that data is going to stay at the edge. And when it comes to disadvantages, it's CapEx heavy. We're very much used to a model nowadays in the cloud, which is OpEx and spending money on a rental basis, on a monthly basis, based on demand. And unlike that, we're now looking at in the edge to have to deploy expensive hardware potentially that could cost a lot of money. So switching that model could present some challenges in terms of CapEx costs. Security becomes your responsibility. As I mentioned, that could be an advantage if you manage security very well. But also with the cloud, we've become accustomed to letting cloud providers manage the network layer and the physical layers of security. And now that becomes your responsibility if you're deploying things at the edge. So if that's not being taken care of and you're not thinking about physical security as well, that could become an issue at the edge. When it comes to additional management and maintenance, you could be managing potentially thousands of devices at scale, depending on what your company does and how you use IoT devices or edge deployments and things. And that becomes challenging when it comes to upgrades and patches and things like that, and managing those devices. I know Dinesh is going to cover that in a bit more detail. And then scaling on demand becomes a huge problem, because in the cloud, you almost have an infinite amount of resources. You're able to take advantage of things like auto scaling as well. And when you deploy at the edge, there might only be a finite amount of capacity that's deployed. So how do you handle scale and getting access to new hardware and things quickly? And lastly, data loss. And this is more because a lot more compute-focused workloads are generally running at the edge, and discarding the data, almost processing at the edge and keeping the data it needs, but discarding the data that it doesn't need, and not necessarily sending it up to the cloud. So if we're not sending that data to the cloud, or we're not storing that with large volumes of storage at the edge, is there a risk to losing data that we might later regret that we should have kept? So it's very important when deploying at the edge, understand what data you need to keep and what you can discard. So that could become a challenge. So at this point, I'm going to hand over to Dinesh, who's going to do the deep dive. As I said, he's the techie one, so I've just done the light touch stuff. He'll dive into some use cases around edge, the challenges, some deeper on the challenges that we face with edge computing, and also things like deployment to the edge as well. So I'll hand over to you, Dinesh.
Thank you, Mark. Yeah, I know that you tried to rush through your stuff, and I think we're pretty much on time. So thank you for that. Leaving me 30 seconds to go through all of my slides. We've got the challenge of Mark running the slides as well, so we'll see how well that works. So Mark's already mentioned some of the use cases for IoT devices, but got a couple of quotes here from Gartner and where they're predicting IoT and in particular edge processing to go over the next 3-4 years. So there's going to be a huge increase, 150 billion IoT devices out in the world. And that's not only smartphones and smart speakers, but if you start going into smart homes, you're thinking about locks on your doors and on your windows, potentially smart alarms. That could grow massively. And in a sort of commercial space as well, you go down into factories and all of the robotics or sensors and cameras. And then you go even wider into smart cities and sort of getting traffic lights and anything like that connected together, or starting to collecting environmental data across a city. There's going to be a huge explosion in the number of devices. What's really interesting as well is on that second quote about the amount of compute and data processing that's going to happen. So 90% of that at the moment is done in a cloud or centralized data center location. And over the next 3 years, we're going to shift that so that 75% is going to be done at an edge location. What kind of edge that is to be decided, but there's some real value and some real industry movement towards getting processing out of a centralized cloud area. I guess some of concrete examples that we can go through, got some images here. So we are talking with a company that's doing work in a greenhouse at the moment, and they're assessing plants and how well plants are growing across a greenhouse. So currently this is a manual process, but they're looking at putting cameras around the greenhouse with some machine learning algorithms to start tracking how well plants are growing and then reporting back. They can then feed that back into things like watering cycles or the amount of fertilizers that go in certain areas of the greenhouse to make sure that things are growing as well as they can. The other one that I want to touch on that's fairly close to home that you might not think is an edge device is your automated cars. So they're processing and gathering a huge amount of data to keep you safe on the road. And what people might not know is that brands like Tesla are gathering and storing all of that information and using it not only to drive, but they're then uploading all of that information to the cloud to be used as part of training models. So there's a definite interest of moving processing to the edge to get you that speed and that safety, but also this hybrid approach of having more complex machine learning models and big number crunching of data being pushed up into a cloud location. So there's a real split there between the latency requirements and the speed of reactions in a car versus the amount of data processing that you can have. The other one that I wanted to touch on a latency specific use case is on looking at production lines or quality assurance in factories. So rather than this being done potentially either by hand, you could be getting a camera here that's looking at a belt of apples here going past a sensor, and then having a robot picker that's picking out the bad apples. I had to put that in there, sorry. So that, again, latency is absolutely huge. And some of even the short latencies of going up to a cloud become really problematic, and you start having to slow down the conveyor belts to then get the processing that you need to do. So I guess some of the challenges that we're looking at, though, on the technical side at least, is how do we get deployments working? How do we manage the hardware? How do we then roll out all of our changes? And one of the key things there is intermittent access. So if you think back to a car, you can usually, if you're in a city, trust that 5G or 3G is going to be able there to give you some communication. But if you're out in the middle of a desert, you're not going to have that. So you need to be designing your edge applications and your edge processors for something being offline for a long period of time. And then when it comes back into connectivity, what are you going to do? Are you going to be prioritizing uploading data or doing software updates or downloading more containers? So there's a huge different way that you need to think about application design and application deployment. Going on to the great thing about Kubernetes is that it's answered a lot of these questions for us. So we're already designing applications with failure built in, right? You treat a pod as if it will go away at any point and restart. So that's a really interesting thing and a really good thing. From a consistency point of view as well, we're trying to aggregate what a node looks like. And it doesn't really matter if it is in cloud A or cloud B or cloud C, the same container can run everywhere. And that hardware independence is really, really key. The next thing kind of I want to cover is different ways that we can deploy or architect edge locations. So this is kind of the most simple way of doing it, where you treat each edge as its own Kubernetes cluster. So you've got full control planes, etcd, whatever you're using to back everything up in each edge location, and you're deploying it alongside your workloads. So this is really good when you've got a decent sized amount of compute resources, or you've got some resilient hardware that you can put in an edge location, and you can have the ability to keep these edge locations online on their own. With this architecture, if the connectivity to Edge 01 disappears and it falls off the internet for a period of days, everything that's running there will carry on running. You've got the benefits of Kubernetes restarting workload and restarting pods and giving you the benefits that we have there. And then when it comes back online, you can then get new manifests and new containers. You can also start putting things like caches in place as well, so that if you're downloading and distributing images across an edge location, you can have it a similar deployment pattern across the entire edge architecture. However, this doesn't always work. So The next pattern is when you don't have enough resources at your edge location to run all of the control plane infrastructure. In this case, the architecture pattern here is that you've got a centralized control plane that's running your Kube API server and your etcds, and then each edge location checks in as a node. That means that you can deploy things with, say, a daemon set. They're up and running. The kubelet process that's running on the edge node will make sure that it gets restarted, and it will carry on working even if that connectivity between the control cluster and the edge location disappears. But still, you get all of the benefits of having a Kubernetes control plane. This next architecture is slightly similar, but rather than each edge device being a full Kubernetes node, it's only actually running the workload that it needs to. So if you're thinking a smart camera, for example, that could be running only the smart camera application and then checking back into a control cluster. Now, this is where it could be interesting if your control cluster or the control applications could live on a edge node as per the second pattern, or it could be a full Kubernetes cluster in an edge location like the first pattern. So there's some real flexibility that you can have with edge deployments, and you've got to architect it depending on the needs of your data transfer and what you're deploying to. So there are lots of tools out there at the moment that are helping and pushing you towards getting stuff to the edge. One of these applications is K3S. And what's nice about that is that it puts a single process which ties in a lot of the Kubernetes object or processes into a single process. So kubelet, kubeproxy, the CNI lives inside a single process. But what's really interesting as well is it's got this additional tunnel that allows a node to talk back to a central control plane. It also does nice things around upgrades as well in remote locations. So this is one of the options. One of the other projects out there at the moment is KubeEdge, and this does something really interesting around message processing. So while K3s and some of these other edge applications are still reliant on an HTTP call between the control plane and the edge, this actually uses a message bus, and messages are queued in a control plane sort of control cluster. And then when the edge comes online, those messages are passed down to be processed locally in the edge node. And then responses are also sent back across that message bus. This is helping you deal with some of the connectivity issues that you have with edge locations. Another project out there is OpenYurt, and it does very, very similar things as KubeEdge because the problems they're trying to solve are the same. What's really interesting about both of these projects and the other one that I'm going to talk about is they've all identified the same problems, which is that connectivity. How do you get secure connectivity as well across different environments? The nice thing that OpenYurt has as well is this idea of pools. So you can see the red nodes on the bottom right. You could consider edge location 1 and then the purple nodes at edge location 2. So that could be factory 1 or factory 2. And OpenYurt has this idea of being able to configure service deployments and application deployment at a service group level. One of the newer projects out there at the moment is SuperEdge, and this is now starting to wrap some of the health check processes around keeping an edge alive. So there's this light API server, which is not doing health check, but that's doing the caching of responses between a cloud and an edge node. There is the edge health, which is doing those health checks and making sure that you can kind of report to the central location that's there. One of the things that these projects don't do is cover the hardware management. So I just wanted to say that Civo, we are launching a product at the moment which gives an edge management platform with our full Civo stack. So this runs on either hardware that we can provide, or we can run it as a software-only service where you get all of the features of a public cloud and all of the management features at an edge location. So some of the deployment challenges of going to the edge is that, I think I've covered this here, like 1 to 2 is really, really quite hard. And going from 1,000 to 100,000 is relatively easy. The reason behind that is you're designing for failure and designing for failover. And what's nice about going down the Kubernetes route is that we get that out of the box. We're already designing applications for failure. And then same with rollout as well. We are designing with Kubernetes for a consistent deployment that we can put in DR situations, and that can be applied to the edge. We've also solved a lot of problems around monitoring and metrics and observability and sending this data back to a central location. What some of the other challenges there around container size is, again, all about bandwidth, right? We're looking at edge locations that may only have 5G connectivity. Yes, it's really, really fast, but it may only be in 5G range for a very short amount of time. So some of the ways that we can deploy to the edge, this is a pipeline that we'll have seen before. You got your developer pushing stuff to a central cloud pipeline, and then you're using like GitHub workflow, GitHub Actions to push out to each edge, either concurrently or sort of sequentially as you go through. However, this relies on the edges having connectivity when your pipeline runs. And if edge location 2 here is offline as your developer does the push, you're going to get a CI failure, and then you're going to have some of your team working out, right, what do we do in this edge location? Now, for 3 environments, this is probably reasonable, and you can get a team responding to alerts to get things back and running. However, if you've got 10,000 environments, they're going to really, really struggle. So the other way of looking at this is a sort of like GitOps or a pull-based pipeline. So here your developers are checking in config or containers to a central repo, and then you're having your edge locations reach out for configuration options from this central repo whenever they're online. So this is a much, I would say, better. It's a different way of doing the edge, and depending on what you're looking to deploy is something to investigate. I think we've covered a lot of this at the moment, this previously about connectivity. I think that's one of the biggest hurdles that you need to think about when looking at deploying to the edge. Bandwidth being low, the reliability of it going offline. Actually, keeping the edge online is really important and really interesting. So if we take that car example, when it goes out of cell service, the edge node itself, the car is online, and it needs to keep serving data locally, right? You can't just go, oh, my car's lost 3G connectivity, 5G connectivity, all of the automation systems just stop. No, the edge location itself needs to keep running, keep doing what it's doing, even if it's not got any control signals coming back from a central cloud. So keeping the hardware specs right-sized to ensure that an edge can carry on working without a reliance on a public cloud is really, really interesting. And really something you need to consider. And then management and backup connections, either over a cellular or a landline, is something that you need to start looking at. So the edge is here. It's coming very, very soon, either into your environment, but generally it's a lot here. And I think I just want to outline how I feel companies are going to be moving to the edge. So today, we're generally deploying into a centralized public cloud, but we're seeing public cloud vendors start getting edge-specific deployments. So this is where you can get the full functionality or almost the full functionality of a public cloud in an edge location, be that a small data center or you're looking at even some back office kind of things and moving things into an office environment, as we've moved like email servers from your back office into the cloud, and now we're getting compute back into your office and even further. So the next kind of wave is that edge server. So if you're in that office, or take a factory, for example, you probably wouldn't put a full control plane infrastructure in place, but you'd get a couple of servers in a factory with some GPUs in them to do some machine learning that you can then feed back either directly to staff on site or to IoT devices. And then we've got near edge and far edge. Mark, do you want to just cover what the difference between those are?
Yeah, you can do, yeah. Make sure we don't go back to front. But yeah, far edge is more devices like vehicles, autonomous vehicles that might be further away from a connection and from the edge server that might exist in a data center or somewhere. And near edge is where it would be very close in terms of a factory connecting back to an edge server that's very, very close.
Thanks. I know I get those mixed up, so I don't want to bring you in for that. But I mean, the one thing we wanted to end on really is though that the edge is here, the edge is coming, and the main reason for that is that the speed of light really isn't fast enough, and we do need to start going to ludicrous speed. For those of you that know that reference, it's a great movie, and you should definitely see that. But I think we've left some time for questions as well, so if we just want to pull up the comments and see if there are any questions.
Yeah, you do have a couple of questions in there. Vishal is asking, is this possible to achieve running worker nodes only on one region and control plane on another region in EKS?
Absolutely, yeah. And the fact that you're doing it in EKS or in on your own hardware shouldn't matter. Absolutely, you can do that. The idea of something being remote is what's key. The fact it's in a separate public cloud doesn't matter. Okay,
cool. And Valentin had a question too. I'm not sure if you got to that one yet. Do the nodes share resources? For example, some nodes doing processing for the other node? Automotive industry tuned question.
It really depends on workload. So if you're talking about a car, then probably not. You're not looking at a second car on the road to start processing whether or not you should brake or not. But if you're thinking of a factory environment, it depends what your definition of a node is. Because if you're thinking of a camera as an IoT device, that could be sending it back to a set of nodes that are doing machine learning algorithms there and machine learning on the data to then give an answer back to that camera, or even to another IoT device like a robot to pick an apple off a line. So yes, it depends. Maybe is probably the best answer there.
Okay. And was that your last slide? We didn't mean to.
It was, yeah.
Oh, okay.
Yeah, I saw the questions. I took it away.
Yeah, I didn't know if you had a thank you, and here's how to reach us on Twitter and LinkedIn or something like that. But you can post all of that in the chat, and if there's any more questions, if anyone has any more questions for Team Civo, if you all will stick around for a few minutes, you can answer those in the chat as well. But
thank you so much. Thanks for being here today. And we'll kick you out and bring in our next speaker. So let's remove
Thank you.
No, thank you so much. Thanks, Dinesh. Thanks, Mark. Really appreciate that. Super interesting. Loved the slides too. Those were some well done.